Now that we have talked about residuals, now that we've talked about the least square regression line, let's start off by making a definition of what we are dealing with for the rest of this chapter. When I say a regression line, this is what we mean. A regression line is a line that models how changes in the explanatory variable, the x variable, predict changes in the response variable or the y variable. Explanatory, the x, predict changes in the response variable. Thus, the regression line is used to predict the value of y hat for a given value of x. And note, x and y are just placeholders for our specific context of the variables that we'll be using from our data. So the regression line in real units. Remember, in your algebra classes, you talk about lines, and straight lines can often be written as y equals mx plus b. We've known this, we've seen this. In the world of statistics, we use a slightly different notation. So you will see either y hat equals b1x plus b naught, and this is read b naught, or b sub 0, or y hat equals b naught plus b1x, where we know that b naught is the y-intercept, and b1 would be our m, or our slope in this case. We write y hat to indicate that the points that satisfy this equation are our predicted values. And in fact, in statistics, whenever you put a hat on it, we're talking about a model, we're talking about prediction, not the actual values. Notice, all of our x and y values in this case are the actual values that we get. Y hat is the predicted value. The model that is a straight line are our predictions. The more closely the model fits the data, the closer the data values will fit around the line of best fit. The data, the points, will be more concentrated the better fit it is. So we write b1 and b sub 0, b naught for slope and y-intercept of the line. b1 is the slope of the regression line, which tells us how much the response variable, or y hat, changes with 1 unit change in the predictor variable, or the x. B sub 0, or b naught, is the y-intercept, which tells us where the line crosses the vertical axes. That tells us the predicted value of the response variable when the value of the predictor variable is 0, which we know when x is 0, that's where we get the y-intercept. Sometimes it's relevant, sometimes it's not. So in the real world, and your TI and many textbooks use either y hat equals a plus bx or y hat equals ax plus b for the regression equation. It's only important that you keep in mind which value is the slope of the regression line and which value is the y-intercept. You want to use whatever you want. I mean, that's fine. I'm going to use this notation to keep it straightforward, b sub 0 and b1, or b naught and b1. When you are reporting out these two things in context, slope and intercept, I need you to follow these sentence structures to a T. So when interpreting the slope of a regression model, the sentence frame that you will use is, for every additional unit in the explanatory variable, you fill in the blanks, there is an increase or decrease of, give me the number of the slope in the units in the response variable. I'm going to tell you, do not be creative or clever. Do not attempt to impress me as a vocabulist. Just use the given sentence frame or risk not getting credit. I tell you this, and then when you get to the AP test and you don't use this type of sentence and you kind of wing it, you're not going to get credit. And that's the whole goal here. The y-intercept is the predicted value of the response variable when the value of the predictor variable is 0. Sometimes this is a meaningless statistic, and sometimes it is meaningful. What is the cost of renting a car when the number of miles driven is 0? This may make sense, since you may rent the car but never use it. What is the weight of a person that is 0 inches tall? This is definitely nonsense. So sometimes it matters, sometimes it doesn't. Okay, least square regression lines for real units. So in our models, we have our slope, b1. The slope is built from the correlation and standard deviations, as we saw before. Slope, again, is the correlation coefficient times the standard deviation of y divided by the standard deviation in x. Our slope is in units of the response variable per unit of x. Think miles per gallon or dollars per hour. The size of the slope is determined by the units of measure. The size of the slope is determined by the unit of measure. The size of the slope is not a measure of strength or significance. Note that slope is not the measure of strength or significance. It's just the relationship between the two variables. So in our model, we also have an intercept, or B naught. The intercept is built from the data means and the slope. Again, I would put this formula, just like I would put this formula, on your big concept review sheet, along with these sentence structures. So how do you find the intercept? Well, it's the average, remember, y bar minus the slope times x bar. Y bar x bar means our means, averages. Obviously, our intercept is always in units of y. This is non-controversial. Okay, let's go back. If you recall, our high school versus college GPA. We had our scatter plot. We saw it was a moderately strong positive linear relationship with no meaningful outliers that we could see. When we describe this model in terms of its linear relationship, we would have college GPA hat, or that's our model, is equal to 1.1 plus 0.67 high school GPA. Note, there's no hat on our explanatory variable because those are our actual data values. The predicted college GPA for a student with a high school GPA of 3.0 is, if we use that equation, we just plug in 3.0 and we get a 3.11 predicted university GPA. Why would it be good to predict your GPA? Well, you guys are in high school right now. If I want to figure out what you're going to be able to do in college, I need to have some sort of model because I don't actually know what your performance is going to be in the future. The way we describe the slope, and we will do this every time, for every increase of 1 point in the high school GPA, there is a predicted increase of 0.67 points in the college GPA. We can expect a college GPA of 1.1, or this is our intercept. Note, this was our slope, when the high school GPA is 0. Now, if you're having a high school GPA of 0, the likelihood that you're going to college are slim. I'm not going to count that out, but you never know. Now, since regression and correlation are closely related, we must check the same conditions for regressions as we did for correlations. Remember, go back to chapter 7. It's at the end of the notes. We need to check that both of our variables are quantitative, that they are sufficiently linear, and there are no significant outliers. Our data is quantitative. That's for certain. GPAs are both quantitative. The pattern in the scatter plot is sufficiently linear, as we see, and there are some points that could be outliers, but I don't think they're going to significantly affect our model. And so we are satisfied with all three of those conditions, and so we move forward. Another example, suppose we collected the weight of a male white lab rat for the first 25 weeks after its birth. And then we look at a scatter plot of weight in grams and time since birth weeks. It shows a fairly strong positive linear relationship. The linear regression equation models the data fairly well, with weight hat, or our predicted weight, is equal to 100 grams plus 40 times time in weeks. So 1, what is the slope of the regression line? And then explain what it means in context. So think about that for a second. The slope, as you guys know, is going to be 40. It's in front of our explanatory variable. Indicates that as the rat ages 1 week, the model predicts an increase in 40 grams. Okay, well, what's the y-intercept? And explain that in context. Okay, so we look at our constant value. we look at this 100, and that says the y-intercept is 100 grams, which is the predicted weight of the rat at 0 weeks at birth, which makes sense because rats got to weigh something when they're born. 3, what's the rat's weight after 16 weeks? Okay, so if we're using time, 16 weeks, we use our model. Weight, our predicted weight, or weight hat, is equal to 100 plus 40 times 16, which is 740 grams. Okay, we're just doing a little bit of math here. Should you use the line to predict the rat's weight at age 2 years? Huh. Think back to the beginning of this, because I'm going to show you this weird picture in a second. This was over the first 25 weeks of this rat's life. So use the equation to make the prediction and think about the reasonableness of the result. There are 52 weeks in a year and 454 grams in a pound. So if we used this model to predict how much a rat weighs, mind you, a rat living till at least 2, seems kind of strange, but that would be 104 weeks. This rat would weigh 4,260 grams, or approximately 9.4 pounds. This is what you get when you have a rat that lives that long and gets that big. I hope you've never had to see something like that be caught, but that is ridiculous. So the result is not reasonable and highlights the danger in extrapolating a regression line beyond the data. And it's so tempting to be like, this will always be true, so I'm going to apply it forever. And that's just not the case. And I want you to think about Mr. Rat over here when you think about extrapolating past the model that we're given. Okay, this is practice. I do want you to do this on your own, and I am going to do this with you guys as well. I'm just going to pull up my TI-84 and walk you all through this one more time. So we have body weight and backpack. What I want you guys to be able to do is in your calculator, I want you to type in body weight. I want you to type in backpack weight. I want you to find R, R squared, and the formula for the least square regression line, and then describe your results. So if you look at the table that I've already made, I've typed in all of my data. There's only 9, so this should be relatively easy. If you remember, I hit menu, and then I go to statistics, and then I go to stack calculations, and I'm just going to go linear regression, and we're going to stick with our formula of A plus BX. So I'm going to choose body weight to be my X list and pack weight to be my Y list. And I'm going to just hit OK, and it's going to give me what I want. So I have my slope, sorry, my A, which is my y-intercept, is 16.26492733337217. Okay, remember, 16.2649, give me 4 decimals. My slope is 0.090799, so round that up. My r squared, interesting, the first time we've seen this in a little bit. We will get much more detail later, but just follow along with me with the sentence that I write, is 63.15%, and R is 0.7947. Now, switching back to our notes, there is a moderately strong, positive, linear relationship between body weight and weight of the backpack. About 63% of the variability in backpack weight is accounted for by body weight. We haven't seen that type of sentence before. We have seen this one. For every 1 pound increase in body weight, the pack increases by 0.09 pounds, and a 0 pound person is predicted to carry a 16.3 pound backpack. Interesting. Notice we also have our model backpack, predicted backpack weight, backpack hat is equal to 16.2649 plus 0.0908 body weight. Now, switching back to our calculator, if I wanted to add a document and data and statistics, and I want body weight on the Y, I want pack weight. Remember, if I wanted to get my line of best fit, I hit menu, analyze, regression. I'm going to do the same, and I get my model. If I was to find this by hand, on the other hand, remember, to find slope, we take our r and we look at our standard deviation in our y divided by our standard deviation in our x. Those would be just calculated by using one variable statistics that we did in Unit 1. Our y-intercept is using the means or the averages, so we use y bar minus b1 times x bar. I bring these up because the book and the AP loves giving you these summary statistics and asks you to figure these out. So I need you guys to know these formulas because sometimes we are not going to be given the table. Sometimes it's not reasonable if you're dealing with thousands of data and like inputs to actually know what all of the data is to have the calculator do it for you, which is why we're given summary statistics. Lastly, if we look at the plots and draw the least square regression line, now mine's going to look a little different. You can see what we had previously on the calculator. What is this crosshair again? Is if we are finding our mean for body weight and our mean for pack weight, those two means where they cross is going to be on our line of best fit. It's also, if we standardize that to z-scores, this would be the exact same representation. So again, in any good plot, we have labels. We should have our units. Both of these are in pounds. And then we also give our linear regression model. Always, always, always provide this in context with your line of best fit. If you're looking for a challenge, now this is actual data taken from an actual statistics class in a previous year. If you're asked to find the linear model, given the grade from their first test, how well will the first test grade be able to predict their final grade in the course? Now, if I say y hat equals 0.7128x plus 24.8982, the x in this case is the first test, and this is final grade hat. Notice when you don't give that context, you have to do a little mental thinking. Where did each piece come from? That's why we give the context. So if we're asked to interpret this, again, challenge you to type that into the calculator and find these values. R is 0.7846 with R squared being 61.56. Y hat is equal to 71.28x plus 24.8982 with y hat being our predicted final grade and x being the score in our first test. So we should have our model being final grade hat equals 0.7128 first test plus our y-intercept. Now we interpret it using shape, outlier, direction, strength. There is a moderately strong, because of the R, positive linear relationship between score on the first test and the final grade. About 61.56% of the variability in the final grade is accounted for by the score on the first test. Again, this is coming from R squared. More about that in part 3. For every 1 percentage point increase in our first test score, the final grade increases by 0.7128 points. This is our interpretation of our slope. And a 0 on the first test predicts you're going to get a 24.9% for your final grade. That is our y-intercept. Notice how we are slowly building our interpretation to be a wider amount of information. That's why we constantly need to practice this. Now, what happens if you're given the final grade and you're asked to make a prediction about their initial test score? Shouldn't we be able to use this model to go backwards? No. So not the reciprocal. Remember, the regression model gives a prediction for the value of the response variable. We have an input and we're trying to predict the output. We cannot use the same regression model to predict the value of the explanatory variable from the response variable. That requires a new model. You can't just go, okay, here's the y, find out the x. Can't do it. We need to calculate a new model. So the new model requires us to switch the roles of the variable. So instead of s sub y divided by s sub x, we switch. Notice these two are flipped to find our new model. And what is also different, our y-intercept, instead of y bar minus b1 x bar, it's x bar minus b1 y bar. Again, these two are switched. And we're doing this to come up with our model if we wanted to switch the x and y variable. So reversing the roles of the explanatory and the response variable, if we're using body weight and pack weight, would give us this model. Body weight, or predicted body weight, is equal to negative 62.97 plus 0.6955 times the pack weight. So if we find a pack weighing 27 pounds, we would predict a body weight of 124.8 pounds. Let's pause there. There's still a couple more ideas that we have to tease out and unpack, and that goes back to residuals, and then from residuals, how we get this idea of variability and R squared, which we've been talking about in the write-ups that I've had. So we're going to pause. We're going to end part 2 here. I want you to practice these problems, practice writing your thoughts out in complete sentences, try some of the homework problems, ask questions, and then we will finish up this in part 3, maybe sneak into part 4 if we need to. See you in the next one, Falcons.